Hey there, I got a question on the video we did with, it was the Newton's method, but instead of solving for the implied volatility, we assumed that the implied volatility was given to us, and we wanted to solve a stock price. Maybe you have a model, you think the implied volatility is more accurate, and you want to work out a stock price for it. I'm not quite sure why you would want to do this, but that was the request. So we built that in Python, but there was a request for the same thing in an Excel spreadsheet. And the transformation from implied volatility to solving for the stock price is pretty straightforward. We talked about that before, and we've talked about Newton's method before. So I'm just going to blow through this very quickly, and I'm going to link to the videos on our original Newton's method if you're curious what the hell that is, and the original spreadsheet for the implied volatility video. So yeah, let's just jump into it. Okay, so this was the spreadsheet we put together well over a year ago that calculates the implied volatility. So the unknown obviously is the implied volatility, and since this is Newton's method, we need a derivative of our function, our objective function with respect to volatility. Well, that's just vega. So if we wanted to redo this in terms of having our stock price as the unknown and volatility as the known, we would need the derivative with respect to the stock price, which is just delta. So to translate this over to what we did with the Jupyter notebook, all we would need to do is replace the formula here, which is vega, with delta. And then essentially all we need to do is interchange the columns, the stock price here and the volatility here, and then make sure all of our formulas are adjusted accordingly. So let's just do that. Let's start off with a new spreadsheet. Okay, so OBS is not going to let me switch between windows that easily, so I think I fixed the problem here. And let me just paste in our column headers from the last video where we have implied volatility. Let's just expand this out a little bit. Our stock price, days to expiration, risk-free rate, the actual price of the call, and I'm going to do this for calls too, so you're going to have to adjust the formula if you want to do puts. We have vega, we have our D1, D2, and vega. So we're going to need to, I'm not sorry, this is volatility, not vega. We need to replace this with delta. We would replace our volatility with stock price. And we would replace the stock price here with volatility. And now we can put in our numbers. And what I'm going to use is the numbers we used in our Jupyter notebook when we did this problem. So our strike price was 135. Our days to expiration, remember this needs to be in years, so it's 14 days divided by 365 days per year. We took the risk-free rate as 1% annual. The actual call price was $1.70. And our volatility was 0.6427. And when we did this in the Jupyter notebook in Python, we took our initial guess at the stock price to be 100. So now all we have to do is compute the D1, D2, and delta values for these parameters here. So what I'm going to do is just copy and paste the formula from the previous notebook and then interchange the A column and the stock price column. So this should be the correct formula, and there we go. We get a number that's kind of silly because this stock price is actually way off. Now let us calculate our D values, our D2 value, and that is simply that. Let's run it to make sure it makes sense. Good. So our delta is just why do I always want to say continuous? It's cumulative distribution function of D1 for a call option. So this is equal to norm dist. Our D1 values are what? The G2 column, G2. And it's mean 0, standard deviation of 1, and we want cumulative, so we set it to true. Okay, now for this update, remember the update is equal to the negative of the function we're trying to find the root of, which is our our objective function divided by its derivative, and then we just add on to it the current estimate. So our objective function, recall from the old notebook, is just basically the Black-Scholes call price minus the call price of the actual option. So now let's go back to the spreadsheet itself and implement this. So this is going to be equal to minus our Black-Scholes call price, which is this guy. And then we're going to subtract off our actual call price, which is this guy. We need to divide by the derivative, which is our delta. And that should be it. Now we just add on our original guess of the stock price. And it looks good. So now we just build our iteration. So I'm going to come down here and do a stock price here. That's going to be equal to this fellow over here. And I'm just going to pull all these down a few. Just duplicate all these numbers. There we go. Let's do the same here. And lastly, here. So it looks like we've converged here to some sort of consistent answer. This is 120.93. This is 120.93. Let's go back to the Jupyter notebook and see what the actual value we calculated there was. Here we are, and we got 120.93 in about 6 iterations. What's the, how many iterations did we do in the notebook? Well, I did 8, but yeah, close enough. Excellent. So this is what I'm going to actually upload to GitHub, but just for the sake of completeness, let me just delete that, and let me even delete this this value here. You could, in principle, use a goal seek type of function to do the same thing. I just wanted to implement Newton's method, so I did that. So if we come to our data tab, go to what if, goal seek, we can set our Black-Scholes price here. Set it to the value that's equal to our call price, which is here, this 1.7. And by adjusting the stock price, which is this cell here. So if I hit go, you notice that this converges to 120.93, which is what we want. So that's probably the way to do it in practice. It's just I wanted to implement Newton's method as per the request, so that's what I did. So I'm going to undo all this. Undo, and this is what I'm going to upload. Okay, so I noticed OBS did not pull in the goal seek window itself. I don't know what happened there, but you know, there are only three fields to fill out, so it's pretty straightforward. Yeah, just a quick video today. Until next time, see ya.